do this. You know what? Let's just stop trying to do it at a lower level of abstraction. We'll just take advantage of Vivado. This is where having a high level language is good. If then we need to have new input. If load okay. Yeah, I kind of lost my patience in trying to show you every single little detail down to the gate level. So we're gonna just take advantage of Vivado's high level programming. So pretty much we're gonna do if load, then it's gonna assign the n value to x, and then down here it's gonna assign the x value to the LED. We cannot assign it directly to the LED. We cannot assign n to LED directly because LED is not registered. You have to do x first, an internal register, and then use an assign statement. Like our load button. So what am I doing? Yes, we didn't really need the Mux module, but I guess you guys learned a new trick from seeing how that gets made. Log divider, we need that though. And this right here, this is very reminiscent to the structure that's going to be in your lab. I tried solving this whole problem a different way, but just to make it not too similar, so it won't be too incredibly easy. But yeah. Except that it would be too complex to do it all manually. So just doing a simple if statement will just literally have it all just happen. See if it worked. So, It wasn't working, so let me see if that fixes it. Oh, what? Wait a minute. Oh, so it was working actually. Oh, fascinating. Okay, so yeah, it kind of worked. Um, oh darn. So so yeah, like from before, press the this button here is the enable. So when I press it, it starts counting. These two switches are the turn light. So these two switches are the things we're going to load in. So if we load in 0, we have to press the enable, and if we hold in, because it's going to count up, but if we do that, this button right here too is the load button. So if we press both the load button and the enable button, it will set it these two LEDs to be equal to the binary value of these two switches right here. So if we set it to 0 and we hold both down, it'll go to 0. You see how it skipped the last one? Like if we just do it normally by holding down the enable, it'll count up to 3 and then go to 0. But if you do that and hold both down, then it doesn't. So it was just it works. It's just a weird implementation. Let's see if that changed anything. It should still behave identically. And then press the other button. Just gonna hold it down. Okay, yeah, it's not doing anything. So I'm gonna let go that one and just have the enable. Works. Okay, so yeah, this actually worked. Yeah. Definitely have to edit this video, cut out a bunch of stuff, make it shorter for you guys. Oh, so yeah, that's that. And one last thing I have to show you guys. Okay, so this thing right here, this is an extra credit opportunity I made. It is not, it is kind of complex because it involves understanding everything down to the gate level. It's not like this, you just write one singular statement and then you let the compiler do all of the work for you. You have to actually do the circuit design yourself. Your lab will be like this. There's going to be like 5 if statements and you just have to write in the thing that's supposed to be in there. It'll be very easy. But this right here is very complex. So if you can do this, you'll get a lot of points. So yeah, it's the 2-bit counter. It can only count up. The counter already has an enable switch and a button to enable the load. But this is the load enable, the load bits, and the enable switch overall. So make a B where it toggles between counting up and down. And then we want to redo the entire thing to make it be 3-bit. Yeah, it's a lot. So a hint would be to redo this and this for what it would be if it was a down counter. So you'd make a whole separate truth table with the next states and everything, do the K-maps, get those two things, and then what you do is you would have those circuits there, and then you have there be like a mux, another mux in between here to control what comes from here to here, and then from here to here, and then yeah, that would be that. And then once you figure that out, doing the 3-bit one would be super easy since it's just doing the entire thing again, but with a bigger truth table. And yeah, so if you can figure this out, you'll get pretty good extra credit because this is not at all easy. I mean, it's easy, but it just takes time and deep understanding. Like if you can understand this, you can understand anything. Okay, so yeah, that's that. Just gonna begin editing this video now. Alright, see you guys later.